Hi everyone. So I'm excited to be here. So I'm sorry if my title is a bit confusing or sounds bold, but these are actually two different things I'm talking about. So it's about understanding question comprehension, and then generalizability and transfer learning are two different things. So just to give an overview of what's coming, so I'll quickly introduce myself, what I have been doing so far in terms of where I've been and my research, and I'll talk about two projects that I've done, which are related both in the area of deep learning and which are relevant to the work that you might be doing here. So I began studying computer science at IIT Bombay in India. And then I went to the Max Planck Institute in Tübingen to work in a bioinformatics lab, where I was also working on machine learning related problems. After that, I decided to go back to doing like core machine learning instead of bioinformatics. So I did a master's at Saarland University, where I wrote my thesis on computing balanced graph cuts, so multi-class clustering. And since 2014, I have been doing my PhD at the University of Chicago, and during the course of which I have also done internships at Amazon and Google. And all the work that I'm presenting now is in collaboration with Google, so it's a long-term collaboration during the course of my PhD. So I've worked on mainly two kinds of things during my PhD. One is extracting hierarchical structure from data using matrix factorization. I guess I'm blocking the screen. Extracting hierarchical structure from data using matrix factorization. So think of data that comes from social networks, or like similarity matrices or circuit simulations. The matrices that arise in these situations are not low rank, and we cannot use traditional like low rank modeling assumptions to like either compress the data or try to like do matrix factorization or to interpret it. My advisor started working on this other alternative to low rank assumption, which is hierarchical structure, and he started proposing a factorization for symmetric matrices. So this is related to harmonic analysis and essentially building a wavelet basis on the space of functions on the range of A. I'll not go too much into detail, but I have been working on developing efficient algorithms to compute these factorizations and to use it in various scenarios, such as compressing large matrices or accelerating linear solvers. More recently, I am trying to extend the factorization to generic rectangular matrices, and potentially using that to compress neural networks. The other part of my work deals with understanding what neural networks learn, and this is going to be the focus of my talk. So this falls under the realm of interpretability and discovery of failure modes of neural networks, constructing adversarial examples, doing rule extraction, and repurposing trained models to new tasks. So any question about the matrix factorization part? Okay. So the first thing I want to talk about is our upcoming paper called K for the price of 1. The context for this is the following. So we are doing lots of deep learning. We are using it for more and more tasks, and a lot of the computation is moving to devices for good reasons, such as enabling better privacy or faster response times or scope for personalization. This comes with a lot of challenges, such as model sizes being increasing, and as we want to solve more and more tasks using deep learning, the storage space for all the models also increases. And there's a lot of effort into compressing neural networks to get with the minimal reduction in accuracy. We go at this from a different angle, where we ask, can multiple models share parameters? Share most parameters, in fact. So this brings us to transfer learning. With deep networks, there are mainly two ways in which people do transfer learning. One is called last layer fine tuning, wherein you have a pre-trained model on task A, and for task B, we fine tune the last layer on the new data set. And this works for very similar tasks when the data sets are very similar, and essentially we are relearning the linear classifier on the new task, but not really changing the embedding space. And sometimes the last layer can also be very large, such as in MobileNet, it's 37.5% of the total size of the network. Now, when this doesn't work, people resort to full fine tuning, wherein the pre-trained model is simply used as a warm start for the new data set. Now, this may work well, but it can overfit when there's less data, or it in terms of storage space, it doesn't help because we have an entirely new set of weights to store. So, what we do, we propose is the following. We propose using a model patch on the pre-trained model, so that the model works on the new task. So, the idea is to insert these layers in between, which are typically very small, and we fine tune only the patch layers for the new task. So, in this case, only the orange layers are fine tuned on task B, and all the blue ones are simply copied from task A. So, one example of the patch is simply adding a scale and a bias parameter over every activation in the network. And there are some advantages to this, since these layers are by design very small. We have a very small increase in the number of parameters compared to last layer fine tuning, but we get like pretty good performance in terms of accuracy. And most of the time, these parameters can be absorbed into existing layers. For example, scale and bias parameters can be absorbed into batch normalization. And in the paper, we also show that how the embedding space, by embedding space I mean the activation space here, changes compared to simply doing last layer fine tuning. So, these are some results. So, here we have inception network trained on ImageNet, and we want to make it work for different data sets such as flowers, cars, or aircraft. And we see that when we only fine tune the scale and bias patch, which is the SB only row, and fix the last layer to random weights, we already get pretty good accuracies. And compared to last layer fine tuning, like in this case, the accuracy here is even higher. And we see that when we combine last layer and the scale and bias patch, then the resulting accuracy is even higher, and in case of flowers, it's comparable to doing full fine tuning on the network. And when it comes to number of parameters that we are adding or training, that is very small compared to what we need to do in full fine tuning or the last layer. So, here is another example where the tasks are completely different. So, the first task is basically drawing bounding boxes around objects in a given image. We use this network called Single Shot MultiBox Detection, or SSD network, which uses the MobileNet V2 as architecture as an image featurizer. So, we take that part, add a last layer on top, and make it work for ImageNet. So, in this case, we jump from 29% to 47% when we add the model patch along with the last layer. And just to illustrate how powerful the model patch can be, here we are trying to take a randomly initialized MobileNet network. So, fixing the random weights and training only the model patch on ImageNet. And with both, when we only fine tune either last layer or the scale and bias patch, we get very small accuracy, but when we combine those two, we get 20% accuracy on ImageNet. It's just an illustrative example. So, I mean, clearly, here transfer learning has good accuracy, but it certainly doesn't match when compared to full fine tuning. So, we would like to be able to change the other weights as well. So, we take this idea to the next level by doing multitask learning. So, the setting is as follows. So, we have these two models that share most parameters. Now, this diagram is not to scale, but the idea is that these gray layers are the weights corresponding to these gray layers are shared between the two tasks, and they comprise more than 90% of the network. And the blue layers are the model patch for task 1, and the orange layers are the model patch for task 0. The idea is that both worker 0 and worker 1 send gradient updates to the gray layers, whereas for the blue layers only receive gradient updates from worker 1, and orange layers only receive gradient updates from worker 0. So, the idea is that by allowing these gray weights to be affected by all the data sets or all the tasks, maybe we are able to boost the performance. So, we applied this to domain adaptation, wherein we have 5 MobileNet V2 networks training on ImageNet, but at different resolutions of images. So, we train all these 5 networks simultaneously. It uses a lot of computational power to train them, but the end result is that we only have to store a little more than a single network's worth of parameters, but we have 0 loss in accuracy compared to independently trained models. In these two cases, it's marginally higher even. And this is the column when we share all the parameters. So, all the layers are gray, in which case there is some loss in accuracy. So, this is an example where transfer learning doesn't work that well. So, we have 47.5% when we take a mobile network pre-trained on ImageNet to make it work for the Places 365 dataset. But when we do multitask learning, then we have no loss in accuracy, and we only need to store a fraction of the number of parameters as compared to independently trained models. So, to recap, we have seen a novel technique to efficiently transfer pre-trained models to new tasks. The advantage is that we are able to store many models in almost the space of one. We saw how the idea of a model patch can be used to customize a given model to different tasks at low cost, and we also saw how we can use this in multitask learning and get very good accuracies. So, any questions about this so far?
So, the interleaving layers that you fix are trained with a particular input distribution, and you're changing this input distribution. How do you reconcile this fact in your proposal?
So, the question is, so the blue layers are trained with a different distribution.
So, yeah, when the parameters were trained, there was like some input distribution that
Yeah.
you were exposed to.
Yeah.
And now in the new model, this distribution changes.
Yeah.
You're not changing the parameter weights.
Yep.
So, I see this as like a potential problem.
It is a problem if there is a lot of memorization, but in some sense, the fact that this transfer learning works is testament that some of these layers might be learning things that are pretty general, which are valid across data sets, like edge filters, for example. They are relatively independent of the data set.
But it works better when you tune them as well, right?
Of course, it works better when I allow both distributions to affect the shared layers. Yeah, I mean, it's a good question. I think it would be interesting to see, to be able to maybe quantify or characterize the effect of the distribution on the transferability more.
have you tried using residual connections to like reduce this effect? I guess.
No, I haven't. I have tried this on ResNets. The results are similar. Was that your question, or?
I meant like instead of only feeding the previous layer directly, you can also provide an alternative way for the input of the fixed layer to also consume the previous fixed layer.
I see. Yeah, it's an interesting idea. Haven't tried it. Yeah.
In the transfer learning experiments, there seem to be two data sets, but the task is same, right? Image classification. Have you tried multiple tasks, like image captioning or object detection?
I haven't tried that, but that's in the agenda. Yeah. Any more questions? Okay. So this is coming to the second part of my talk. If anyone has seen most of this already during ACL, I apologize. So this is a paper titled "Did the Model Understand the Question?" And I want to start with this phrase called "Read the question carefully." And we have seen this phrase in exams in one version or another. And the intent of this phrase is that there are some questions in this exam, and they are going to look similar to what the students have seen in class, but there are some key differences. So it's telling the students to read the question carefully because the differences are important in answering the questions correctly. So in this context, the students are these three question answering networks, and the tasks are as follows. So there's a natural language question and a context, which may be a table or an image or a passage of text, and the task is to answer the question based on the context. And we consider three neural networks which are close to state of the art performance, and we ask, have these models read the question carefully? So we start with some examples. So here's visual question answering, and there's an image, and the associated question is, how symmetrical are the white bricks on either side of the building? The model answers very, which turns out to be the right answer. So let's start by changing some of the keywords in the question. So if I change symmetrical to asymmetrical, the answer remains the same. Change it to how big are the white bricks, the answer is the same. How spherical are the white bricks, answer is the same. Go to absurd levels such as how fast are the bricks speaking, again there's no change in the model's response. So here's another example. So there's a table of medal tallies, and the question is which country won the most medals. So the way neural programmer answers the question is by converting the question to a table query akin to an SQL query, which it then executes on the table to produce the final answer. And the network itself is supervised on the final answer, and so that the query is implicit in the network. So in this case, it does max on total and does print on nation, which returns the answer Cuba, and that's a good robust table query which will work for various kinds of tables. But if I change the question to which country won the most number of medals, it does max on bronze and returns Argentina, which is the wrong answer. So clearly there's something going on that we want to understand. Why this bronze was picked. So here's another example. Question is, which country performed better, Switzerland or Great Britain? The answer is Switzerland. And how does it happen? So first, the model does select on team. So that highlights all the rows where the entries in team have matches to the question. So in this case, Switzerland and Great Britain. And then it does first, which picks the top row, which is Switzerland, and does print on team. So the answer is Switzerland. Now, if the row ordering were reversed, this program would return the wrong answer. And the network itself doesn't know the ordering of the rows, so it just the way the table is given as input is in terms of the column names and how many matches between the question and the table entries there are in each column. So the model somehow has learned that it's able to get away with doing first. So we want to understand what triggered this non-robust selection.
I mean,
Yeah.
in this particular case, the ordering is actually the ordering of who did the best. So you could argue that for this particular table, it's in the first class.
That's, I mean, we can't assume that, because you can also order it based on the number of matches won, and that might change some of the ordering of some rows.
That this is a table with place numbers.
Yeah.
First place, second place is sort of correct for this table, but it's very low, of course.
Yeah. So, yeah, we want to see something more than just what the accuracy shows us. And this is not a new observation. So, Jia and Liang in 2017, they proposed adversarial examples on reading comprehension models, and their idea was to add an adversarial sentence to the paragraph to fool the model. So there's a paragraph about Tesla. The question is, which city did Tesla move to in 1880? The model answers Prague, and they construct adversarial examples as follows. So they take the question, mutate the question into a fake question by changing some of the nouns and some of the words, nouns and adjectives and dates and so on. They change the answer to a fake answer, combine the fake question and fake answer to a fake sentence, which is then filtered through crowdsourcing to fix for grammatical errors, and then this is added back to the paragraph. In this case, this sentence is added back to the paragraph, and the model now predicts Chicago because it got distracted by this adversarial sentence. So their attacks are very successful over many models, and their takeaway is that reading comprehension models are overly stable, which means that they are unable to distinguish a sentence that answers the question from one that merely has words common with the question. So in some ways, it's relying on trigger logic. And we want to understand how this overstability manifests. Is there some way we can measure it given a new NLP network, and why do their attacks work? Because their attacks are, they are model independent. Given a new model, we don't know. Given a new model and an adversarial sentence, we don't know whether it will attack or it will work or not without actually applying the attack. And in general, how do we go about constructing adversarial examples on new NLP networks in a way that we know that the attacks will work? So our contribution is the following. So we propose a workflow based on attributions or word importances to understand the input-output behavior of networks. So this is a human-in-the-loop process where by analyzing the attributions, we identify weaknesses, and exploiting the weaknesses, we construct adversarial examples. In this process, we also explain and improve Jia and Liang's attacks. So what are attributions? Essentially, we want to characterize the behavior of the model on the given input in terms of the input features relative to how the model behaves in a default setting. So if f is a deep network, we want to characterize f of input minus f of baseline in terms of the input features. And baseline is a default setting for the network. In visual question answering, for example, it would be like the actual input image, but the question would now be empty. So, and there are many methods that we can use. We can use LRP or LIME or many other methods for these. We chose this method called integrated gradients. Essentially, it uses the fundamental theorem of calculus to write f of input minus f of baseline in terms of the path integral of the gradient of f from the baseline to the input. So I won't go into much detail about this, but just say that we picked this because it has good arithmetic justification, and it's also very easy to implement, as we only need to compute gradients, and typically its running time is very low. Now, if we apply integrated gradients to the example we saw before, this is what we get. So, we colored the words according to the magnitude of the attribution. Sorry. So, red and blue both indicate high magnitude, and gray indicates near 0 magnitude. So, we see that the word symmetrical does not get much attribution, and now the earlier behavior of the network when we changed the word symmetrical makes sense to us, because it is not focusing on this word. And we also see that words such as how and either seem to get very high attributions. That is also concerning behavior, because these are words that are not very specific to what this question wants. These are generic words. Yeah.
Is this a property of a trained model? I mean, can you say how do you compute the?
Yeah. So, we take a trained model, and then we compute the gradient of the output class with respect to the input features and do the estimate the Riemann integral.
Question. So the f in this case is the loss for.
Sure. You could. It's just a softmax of the output variable. So in this case, so this visual question answering is considered essentially a classification problem. So we want the softmax of vary. So we take the gradient of the softmax of vary with respect to the inputs.
And you look at vary because it's the correct answer.
Because it's the answer that the model predicts.
So if the model changes its prediction, you still look at the old prediction.
What do you mean changes?
So when you try a different input compared to the baseline, the answer may change, right?
So vary is what it returns in when we pass the full input. When we consider the baseline, even then we consider the softmax of vary.
So the baseline is the one that's modified, the unnatural input?
The baseline is the one where the question is just empty. Yeah, it's a modified version of the input.
I see, okay.
Yeah. So this was another behavior that we wanted to understand about why this first operator was picked. So when we apply integrated gradients, we get this visualization. So the rows are question terms. These are just some pre-processing tokens that the model adds to the question, and each column represents the operator and column selected in the table query. So we see select team first and print team, and in parentheses are the operator and column selections in the baseline input case. Yeah.
Sorry, I'm having a hard time understanding like the intuition behind using the loss to drive this attribution.
Okay.
To characterize the attribution. My understanding is that the larger the loss that goes back to the individual word, it means that this word contributes more to the inability of the model to do this task.
Mm-hmm.
And I don't see the connection. I guess I'm trying to understand why is this the right metric to look at.
Okay. So so in some sense, if we want to understand the influence of a word on the output, normally we would do ablation, right? So we would remove that word or change that word and see if the output changes, right? So taking the gradient is akin to that, wherein we are perturbing the input and seeing how much the output will change. And output in this case is just the softmax of the class that was predicted, like the probability of the class that was predicted. Now, if I remove the word, if I perturb the word symmetrical, how much, if the softmax probability doesn't change much, then it means that the model is not sensitive to the word symmetrical.
And what's the qualitative difference between something that has it's very blue and something that's pretty red?
So blue just means it negatively affects the probability. So if you were to perturb that, then the probability would probably go high. because it used to have a negative influence on the.
So this is like a negative word means that it's preventing the model to perform to get to the right answer. So changing
Yeah.
that word will help the model.
Sure. Yeah, changing the, well, I guess when you're saying right answer, I am not really worrying about whether the answer is right or wrong. I'm only worrying about the model now made an answer. It could be the wrong answer. I just want to know which words helped the model pick this answer. That makes sense?
When you say you perturb the input words like symmetric, are you just perturbing the vector?
Yeah, I'm just perturbing the embedding vector,
I see.
and then taking the gradient on that. Okay, so coming back to this, so we had the questions and the operator and column selections. A few observations. So we see that the word or has high influence on the operators and columns that are selected, and we also see that word better and country seem to affect the selection of the operator first. So even though the default operator is max, which would have been the right operator or the robust operator to pick, because there are words such as better and country, the model is picking first. So these are behaviors that we don't want our model to have, because they'll fail in the real world. Like clearly relying on like the or words such as or is not good. So in general, we want to understand the reliance of these models on specific words, like the extent of trigger logic present in the words, present in the model. So we propose this overstability test, wherein we drop all words from the data set except ones which are frequently top attributions. So we kind of aggregate the attributions of all the words over all the questions in the data set, and we only retain the top few. So questions such as how many players scored more than 10 goals can get reduced to just how many. And when we do that, we get the following. So the x-axis is the number of words in the vocabulary that we allow, and the y-axis is the relative accuracy of the model, relative to its final accuracy. And for visual question answering, we see that just 5 words are sufficient for the model to get 50% of its final accuracy. Those 5 words being color, many, what, how, and doing, which are pretty generic words. So questions such as what is a man doing or what is a woman doing are considered the same in some way. And the important point to note here is that these words are chosen based on attributions. They are not the most frequently occurring words. So the model is really relying on some different patterns that it has figured out. And the story is the same in neural programmer, where about 15 words are sufficient for the model to get 50% of its final accuracy.
Do you have any theories about why it's doing this?
I have some theories. So in visual question answering, so for every image there are 3 questions in the data set, and the model essentially relies mostly on the image and just needs to know the type of the question to predict the answer, and the type can be inferred from just 1 or 2 words. Yeah.
Can you try any baseline for these graphs? I mean, like for example, taking them 5 most frequent words or 5 random words and see how would the graphs look like?
I did not do that. I kind of justified this by seeing that this ordering of words is different from the ordering in terms of number of occurrences of the word. In that case, I would imagine this would not be monotonic. If I just pick words according to the frequency of occurrence, then this might not be yeah, I would not know how to interpret that. Yeah. Okay, so let's see a few adversarial examples. So this one, we just remove stop words from the network, So this is the entire list of stop words that we removed, and neural programmers' accuracy fell from 33% to 28%, and VQA models' accuracy fell from 61.1 to 52. So another attack is subject ablation attack, wherein we replace all the subjects of all the questions in the test dataset with a low attribution noun, so essentially a non-trigger. So in this case, we chose tweet. So what is a man doing becomes what is a tweet doing. We compute the accuracy of the model on this new data set and average that over 10 different low attribution nouns. The idea is that all these questions are now mostly relevant to the associated images, but the model's response remains the same majority of the time. So in this case, 75.6% of the time that it was originally correct.
These low attribution nouns, is that a fixed list or is that specific to each example?
So that's fixed for the entire data set.
Okay. But your attributions are computed with respect to a model and a prediction as an example, right? Or is that not correct?
Yeah, so by low attribution, I mean over the entire data set.
Okay.
So I choose a noun that has never been one of the top attributions. Yeah.
And does you replace the noun with the lowest attribution in the original example? Like, for example, what is the man doing? If the man has high attribution, then changing it would change your prediction.
Yes.
So you pick the noun which has the lowest attribution. On the question side also?
So on the question side, I only pick the subject of the question.
Okay, so even if so it's possible that some of these subjects have high attribution, but
Yeah.
it does not change.
Yeah.
Did you retrain the model or this is only for
This is just inference. So I guess that's the point I'm trying to make, which is that the model doesn't focus on the subject most of the time.
Is that because when people authored the questions originally, they sort of picked the most obvious subjects?
Yeah.
There might be 5 things in the image, but one's more salient, and so they always ask questions about that.
Yeah, that's likely the case, and the model only needs to know if the question is of type what or how many or is there, and then it knows what to answer.
I guess, what would you want the model to say for what is the tweet doing?
I would definitely want a different probability distribution,
Okay.
right? I mean, obviously the model should say I don't know or
Right.
I can't answer this, but if the probability of the answer here is the same as the answer here, then there's a problem.
Did you try training the model on Squad 2.0 or something where nuance is an option?
No, I haven't done that.
When you're saying that the answer is the same, you're not talking about the probability distribution, right? You're just talking about
The max.
the R max.
Yeah. Yeah, the distribution might be different, but it's still the argmax.
And
Yeah.
Arguably, if you gave me a question with a word in that I didn't recognise, I might say, well, I don't know what this is, but I'll still guess at the answer.
Yeah,
So arguably, it's still correct. It doesn't know what a tweet is.
right, but it can still guess something.
Arguably, it's still correct for it to have a guess.
Sure. That's a fair point. Okay, so in this, we are adding meaningless phrases to questions so that the semantics of the question doesn't change. And how do we do this? For instance, for neural programmer, we saw that it answers questions by picking operators. So for each operator, we collected all the high frequent top attributions. And so for max, we see the most and largest, and that looks fine. But for last, we see words like chart, or here there's same, and for first there is who. So there are all these red words that are non-robust triggers for these operators, and we used these words to construct phrases to fool the model into thinking the question is about something else. So we added phrases like in not many words, or if it's all the same one way or another, and the accuracy drops significantly. So neural programmer to 11% and visual QA to 19%. To show that attributions were important in constructing these phrases, we use low attribution words to construct prefixes, and in that case the accuracy doesn't drop by that much. So yeah, coming to Jian-Liang's attacks, just to recall, they mutate the question and answer to fake question and fake answer, combine it to a fake sentence and add that back to the paragraph. So we saw that their attacks are likely to be effective when high attribution words are present in the adversarial sentence, but only low attribution words are mutated. So the idea is that the adversarial sentence is still the trigger, but we want its meaning to be changed by changing the low attribution words. So for example, an attack, so if the question is who was the Count of Melfi, an attack that works has the word Melfi in it. So in constructing their attacks, it would be if we were to use attributions in the crowdsourcing, then their attacks are more likely to succeed. So we haven't done the actual crowdsourcing, but we did some analysis on what percentage of attacks fit that qualification and how much they work, how well they work. Now we want to answer, where do model weaknesses come from? Do they come from the architecture or the data set? So we did a small experiment. So we compared two models. So for tabular question answering, one is neural programmer, and the other what we call KDG, which was developed by some of your colleagues. So in the KDG model, there's still the input and table, but now the supervision is based on the table query and not on the final answer as a neural programmer. Now this model is state of the art on wiki table questions, and it has 7% higher accuracy, and it has a different network architecture. And our observation is that KDG performs well, not only because of its different architecture, but also because the data set is pruned. So when they were constructing these ground truth table queries, they considered different versions of the table, such as by shuffling the rows and so on, to pick the right table query as the ground truth. And when we trained KDG using unfiltered data set, then it did not do any better than neural programmer. On the other hand, when we trained neural programmer using a pruned data set, its accuracy did not increase. So it shows that KDG model works better both because of the data set and the different architecture. In general, it's hard to do data set pruning at scale, and we don't know what is the right kind of pruning to do. So a good way is to look at the data set through the models themselves. And to recap, so we saw an attribution based workflow to look inside and understand weaknesses of a model, and we understood how trigger logic manifests and that question answering networks do not learn the right triggers, and we saw how we can construct effective adversarial examples and improve Jian-Liang's attacks as well. In general, attributions are simple tools to understand what models are doing, and they can help us with enriching the data set or adding constraints to the network to steer the model away from like non-robust behaviors. And I guess overall we have seen two kinds of results, one where neural networks rely on trigger logic and miss semantics, but on the other hand neural networks are also able to adapt to new tasks. So I guess some things I have in mind for future is to try out the transfer learning technique on NLP tasks, and maybe use the transfer learning as a way to improve robustness. So one idea is to develop like a robustness patch for a given model, wherein we would just do transfer learning on an adversarial data set, which makes the model more robust. Another direction that I have been working on is to understand the different ways in which a given word influences the answer. So does the word influence the answer through synonymy, or through through its role in the grammar, or trying to understand if we can characterize or separate that via attributions. That's something that I've been trying to do as well. So thank you. That's the end of my talk.